Carl Friedrich Gauss. So this would be n times the quantity n plus 1 divided by 2. And of course this one now is just simply n. And let's see what we've got. The 2 and the 4 are going to cancel. And so we end up with 2 divided by n squared multiplied with n squared plus n. And then we have 1 divided by n squared times n, so that's 1 divided by n. Although I think, in looking ahead, that if we leave that as n divided by n squared, we have 2 fractions, same denominator. So we have 2 times n squared plus n, plus n, all of that divided by n squared. 2n squared plus 2n plus n is 3n divided by n squared. Factor out an n, 2n plus 3 divided by n would be our answer. We could also say that's 2 plus 3 divided by n if we break this into 2 fractions. Now we're not done with the problem. It says n is 10 and n is 100. Let's go back and just look at that one more time so we don't feel like we rush through this. Once again, if we are looking at this, we can divide it. This is a constant, so we can bring it out in front. We can then take the summation of a sum or difference as the sum or difference of 2 summations, so I break it apart. I see that 4 is another scalar, so it comes outside. This then becomes Carl Friedrich Gauss's problem. This is one of those properties on about the 2nd page of these notes. So if we have the Carl Friedrich Gauss problem, we take the number of terms times the number plus 1 divided by 2. This then is just 1 times n is just n. 2 divides into 4. I have 2 divided by n squared times, and then I have n times n and n plus n times 1. I opted to take this term times n and leave it as n divided by n squared so that I have 2 fractions with the same denominator. With that in mind, we can add those. I multiply 2 through that, and then 2 times n plus n is 3n. Factor out the n, cancel with one of the n's in the denominator, and then if need be, and I think we probably want to do this at the very end, we can make this 2 fractions. Because it says, what is it when n is 10? So the value when n is 10, so s of 10, would be 2 plus 3 divided by 10, or 2 and 3/10. When n is 100, we would have s of 100, and that would be then 2 plus 3 100ths, or 2 and 3 100ths. Okay. The next problem is doing basically the same thing. Find a formula. Use the formula to find the limit as n goes to infinity. So we're going to take the number of rectangles, so to speak, because this is what we really are looking at here. If we have the limit as n goes to infinity of the summation of n terms, we have 1 plus 2i divided by n quantity squared times 2n. First thing I'd like to do is to make this this first factor into one term. So let's make it the limit as n goes to infinity of the summation of I equaling 1 to n. And if I want this to be one fraction, I would have n divided by n, and so this is going to be n plus 2i divided by n, that quantity squared, times 2 divided by n. Looking at this, the index here is I, which means that n is going to be a constant. I'm going to take I from 1 to n, and if we consider that, 2 divided by n is a constant. If I look at this and I consider that this is also the same thing as, n plus 2i quantity squared times 1 divided by n squared, I have another constant. So I'm going to pull those constants out in front. So I have 2 divided by n. And again, if I square the fraction, it's the same thing as squaring each the denominator and the numerator. And let me rewrite that so we get the limit in here also. So I have the limit as n goes to infinity of 2 divided by n times 1 divided by n squared, then times the summation, I goes from 1 to n. Again, I is the thing we have to keep looking at here. And the only thing I have left over here is n plus 2i quantity squared. So if I look at n plus 2i quantity squared, I can simplify that. Let's see, this is 2 divided by n cubed. And then I have the summation as I goes from 1 to n. And this is going to be n squared plus 4in plus 4i squared. Now this is the summation of the sum or difference of numbers, so we can write that as the limit as n goes to infinity of 2 divided by n cubed. And then I have, let's put that in parentheses here. Let's see here. Let's do it this way. We're going to get a couple of parentheses if we're not careful. And so I'm going to write this as the summation as I goes from 1 to n of n squared, plus the summation, let's see if I can get that drawn a little better there, plus the summation as I goes from 1 to n of 4in, plus the summation as I goes from 1 to n of 4i squared. In the same reasoning as before, the n squared is a constant. In this one, the 4 and the n are constants, and over here the 4 is a constant. So I'm going to pull those constants out. So I have 2 divided by n cubed, and I'm going to have a constant now. Now remember, when we have a constant in a summation, though, it's going to be the constant, and if I pull that out, the only other factor left here is a 1. So I have n squared times 1, so I pull the n squared out because it's a scalar, plus 4 times the summation as I goes from 1 to n of I, because I'm going to pull the n out also, plus the summation, oops, let's try that again, plus the summation as I goes from 1 to n, the 4 comes out as a constant, and I have I squared. What I'm hoping to do, and what I think we've achieved, is that each of these now is one of those shortcuts, those patterns we saw in about the second slide of this lecture. So I have the limit as n goes to infinity. I have 2 divided by n cubed. And in here now, I have n squared, and I need to look at what is the summation of a constant as I goes from 1 to n. As you recall, it's the constant times the number of terms, plus 4n, Carl Friedrich Gauss, adding up terms from 1 to n, so this would be n times n plus 1 divided by 2, plus 4, and looking at our shortcut or our pattern for I squared, it's n times n plus 1 times 2n plus 1 divided by 6. Now we've written this without any summation. all we have to do now is take the limit as n goes to infinity. Before we do that, though, we're going to simplify this as much as we can. Let's look at, we'll keep it a little simple here. I'm going to continue to write my 2 divided by n cubed out here. This term, n squared times 1 times n, is n cubed. This term is going to be, let's see, this is n squared plus n. Also, our 2 and our 4 can cancel, so this becomes n squared times n plus 1. So let's see, that would be n cubed plus n squared plus 4 and 6 have a common factor of 2. So we can factor out a 2 from that. So we end up with 2/3. And then we have okay, forgot my 2 back here, didn't I? So we'll squeeze that 2 in there. And then we have 2/3 times, let's see here. I've done some collaboration, some other things. So let me back off here and just write what I have on my notes, and you can verify whether or not they are correct. I have 4/3, I'll put these in parentheses here, 4/3 n cubed plus 2n squared plus 2/3 n. And that would be coming from that term, this would be coming from that term, and so forth. What we have then is the limit as n goes to infinity. And we're going to end up with all of this. Let me just do this. We're going to end up with the summation of, and you can verify this, 26/3 plus 8 divided by n plus 2 divided by 3n squared. What I did was I collected like terms, multiplied through, found a common denominator, etc., 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 simplifying all of this with algebra. Then the only thing we have left to do is, what do we do when we take n to infinity? Well, these terms, these last 2 terms, are going to go to 0 because the denominator is increasing without bound, and our answer is going to be 26/3. And this would be 26/3 square units if we're talking about rectangles. Okay, the next